So we have the last presentation of this session. The title is Survey of Approaches for Emergency Landing Spot Detection with Unmanned Aerial Vehicles. The authors are Gabriel Loureiro, André Diaz, and Alfredo Martins. And the paper will be presented by Gabriel Loureiro. Please.
Hello, everyone. Thank you for the introduction. I will be presenting the paper Survey of Approaches for Emergency Landing Spot Detection with Unmanned Aerial Vehicles. This is the outline of this presentation. First, I will present the motivation of our proposal and formulate the problem of detecting landing spots. Then I will explain some existing works in the literature related to this topic. After that, I will present our proposal and show some results. Finally, I will end the presentation with the conclusions that we've made and our future prospects. The research and use of UAVs has been increasing due to applicability in a large set of tasks, such as search and rescue, delivery, surveillance, inspection, and interaction with their environment. However, these vehicles are susceptible to external disturbance or electrical mechanical malfunction. For instance, a UAV doing a delivery operation may have some battery failure. In this case, the vehicle must safely land in a spot that will minimize damage to the robot itself and won't cause any injury to humans. Hence, considering these conditions, the reliability of a land spot depends on two main factors: the distance to the vehicle and the ground conditions. In terms of ground conditions, we can consider information that may qualify the terrain, such as the slope of the plane, the roughness of the area, the size of the spot, and the presence of obstacles. With that being said, there are considerable works related to the land spot detection in the literature. In terms of LiDAR-based techniques, we can mention the work developed by Sebastian Chia in 2012, where the point cloud is processed to create a regular grid for evaluation of land spots. In our project, a knock tree is used to structure the point cloud, speeding up the neighbor search. In 2015, Daniel Maturana developed a 3D convolutional neural network to differentiate between the low vegetation and obstacles. Our approach is going to analyze the geometric features without needing to train the algorithm. In 2017, Oscar Lorenzo developed a land spot detection by processing the point cloud in parallel on many core systems, based on a tree and geometric features. In our approach, we are going to downsample the point cloud. Another popular sensor to detect landing spots is cameras. They are lighter and less expensive than LiDARs. However, the applicability of a vision-based technique depends on visibility conditions. In 2013, André developed a detecting land spot method that uses background estimation on stabilized video. And another work in 2015 by Christian Foster developed an elevation map-based technique where the image from a monocular camera and the vehicle's pose are combined to build an elevation map, and this map is analyzed to find a landing spot. Now, regarding our proposal, we developed an algorithm that detects and selects a safe landing spot during the operation. Besides this, the algorithm is periodically reclassifying the detected spots. And as you can see this is the pipeline of our system. It's a set of data processing blocks connected in series. First, the input of our system is the raw point cloud data given in the LiDAR frame. So first we have to transform to the local navigation frame by applying two transformations. After this step, we accumulate the point cloud and wait for one of two conditions to start the next step. One that the travel distance is large enough to find a spot, and the other one that the size of the accumulated point cloud is larger than a threshold. By accumulating the point cloud, we are increasing the computational effort. Therefore, a voxel grid is implemented to downsample the point cloud. The filter takes a spatial average of the points, and the points are then approximated with that centroid. The resulting point cloud is spatially extracted using an octree. In this graph, we are comparing the execution time of a plane fitting in blue and the downsample method in red. Therefore, downsampling the point cloud is justified because it limits the sample size of the point cloud. After that, the algorithm finds the spherical neighborhood of a randomly chosen point and computes a planar surface of the neighborhood points by using the principal component analysis. In this step, a first filtering can be performed by analyzing the slope of the detected plane. If the slope is smaller than the threshold, we can increase the value of the radius and repeat the process. However, if the slope is greater than our limit, we can immediately reject the plane. Finally, when all the planes are detected, we can evaluate these spots according to the radius, the distance to the vehicle, the standard deviation in Z, and the plane slope. For simulation purpose, it was chosen the Modular Open Robot Simulation Engine. The MORPS is an open source simulation that provides several features such as raw supports and are similar LiDAR to the Velodyne PUC. And the simulation was performed on a computer with Intel Core i7 with 4 cores and Ubuntu as an operating system. Here we can see the environment developed in Blender to test the method. The objective of this environment was to test the algorithm in a bad scenario with only a few landing spots. In this video, we can see the red rectangles representing the landing spots, and the blue line is the robot pose. After we pass through the plane, the red diamonds represents the current best spot. And here in this graphic, we show that for several such points, the method was not, however, was not able to detect all landing spots, given the bad environment. We also apply our system to the data set of the monastery of Tbones in Braga, northwest Portugal. In this video, we can see that the red markers are the current best spots, while the axis is the robot's pose. As you can see, as the robot is traveling, we are detecting different landing spots. For this test, we used 2 search points per scan, and the maximum standard deviation for the landing spot allowed was 10 centimeters, and the maximum slope was 15 degrees. Besides this, the radius of the spots ranged from 2 meters to 4 meters. Now, giving our results, the plane detection step of the PCA detected almost 8,000 planes with less than 15 degrees of slope. Of these planes, 2,278 were accepted because they had less than 10 centimeters of standard deviation. And finally, of the accepted spots, 86 were effectively chosen as the best spots. Here we are showing in red is one of the detected spots. In terms of conclusion, we developed a LiDAR-based method to detect emergency land spots after an extensive study of the existing methods in the literature. Our proposal of using a voxel filter shows that the filter can hasten the algorithm. However, our method can fail in a bad environment with a few landing spots. In terms of future work, we are aiming to perform more experimental tests to verify the reliability of our system in several environments. Finally, we're also aiming to compute the trajectory of to the landing spot, and using this as another rating factor to qualify the spot. Indeed. Thank you.
Okay, thank you very much, Mr. Loureiro, for this presentation. So we have time for some questions. Are there any questions from the audience?
I have a question, if you don't mind.
Yes, please.
Actually, I have some questions. How do we recognize the slope? And what if the perfect 0-degree slope is bad for landing? For example, water or deep snow. And how many voxels do you get at this situation?
Okay, but we compute the slope given the angle between the vertical axis in z as 0, 0, 1, and the normal vector of the plane. And of course, one of drawback is that for now we cannot differentiate between a good zero slope or the, as you said, the slope of the zero slope as water or snow. For now, we are not differentiate between these kinds of slopes. And can you repeat the last question, please?
How many voxels do you get?
In the voxel, in the downsample step. Now for now we didn't count the number of voxels.
Okay, thank you.
Okay, thank you. Are there any other questions? Okay, I have a small question. Just to know if you get you have seen that you may have some error in some way. So you have any measure of the reliability of your landing spot? Because if you have a bad landing spot, could be very dangerous for the drone. So just to know if you get not only the possibility but also the reliability of your information.
For now, we are just considering all the parameters that said that to evaluate the spot, we rate the slope of the plane, the standard deviation in z, the distance to the vehicle, and the size of the spot. And of course, sure, it depends on the vehicle. For example, if the vehicle can only land in a slope less than 10 degrees, we can change the value for the maximum slope. And another example, if the standard deviation z is higher than our threshold, we don't consider this spot. We evaluate given these parameters and compute a rate for the spot. And at a given rate, we are classifying the spot given new. Yeah.
Okay, thank you very much. So are there any other questions? Okay, if not, we can thank you, Gabriel Loureiro, for this presentation. This was the last presentation of this session of flying and aerial robots.